All right, happy Monday. We are going to be talking about MIPS instruction set today. We are going to break this up into two lectures. One is part one that we are going to talk about today, and then we'll go over part two on Thursday. That's when your homework one is also due. So a quick recap about the five stages of an instruction. Everything starts with program counter. We have said that many times. Program counter contains the address of the next instruction that you want to work on, or at least you want your ALU to work on. So that starts over there, and you would load that address into the memory address register, perform a read cycle on the memory, and that's what gets the particular address into MBR, memory buffer register, or memory data register, which eventually ends up into the instruction register. Now we will be using this instruction register today. We are going to look at a lot of its details today, so that's where our focus will lie, the instruction register. Now the control unit, or the FSM, is going to look at the instruction register itself. It's going to look at the first few bits that correspond to the opcode, and then the rest of the bits are for operand specifier. But based on the opcode, it is going to send an appropriate the control signals to the ALU to perform that operation. Now, some things like a memory read might be required to fetch one of the operands in some scenarios. So that will go back to MAR. You will do a read cycle on memory and load that particular second operand to the B side of the ALU, and then work on the operation. Maybe that was simply adding the accumulator to whatever is loaded from the memory, and then the results go back into the accumulator, for example. And then if you wanted to store it, you could use the store path with another instruction, right? So this is simply to say that we have a bunch of registers here that are in our data path cycle. But on top of that, we are also dealing with memory, because memory is where all your instructions are, as well as all your data is. Now, if I look at the instruction register, break that up, let's see. That guy essentially has that particular format. I have opcode and an operand specifier. So today the focus will be what kind of opcode, what are the specific, what bits should I have to perform a particular operation. For example, if I'm doing an add operation, I'm doing a load operation, I'm doing a store operation, what kind of opcode will I have? Will the operand specifier be one type, one format, or does it vary depending on the type of instruction? Right, that's what we are looking at. Now, all right, let's move on here. So if you look at the instruction set architecture, which is essentially the interface between the lowest level in the operating system to the highest level in your operations, the hardware, that's where your instruction set architecture lies. And its main ingredients are a bunch of registers. We call that the register file. Now, this is not many registers. They are supposed to be a few in number. For example, in the architecture, MIPS architecture that we are going to look at, we are going to limit it to only 32 registers, each register being 32 bits. And then you have the memory architecture itself. Well, that can be very large, right? So you can have a very big memory, and you would need a lot of bits to identify each address location. So for example, in the memory architecture we will be dealing with it, we will have a 32-bit address used to access an 8-bit location. So the number of data bits at each address location will be 8, for example. This is again the memory architecture that we are considering as an example. So let's say we have a 32-bit address. Here we have 32 registers. Here we have a 32-bit address. And at each address, you have 8 bits. Then, apart from the register file and the memory architecture, you have the instruction set itself, where all the details about the instructions are laid out. For example, what are the operations? What are the instructions you can carry out? Add, subtract, multiply, load, store. You can do a lot of logical operations, and or you can do a lot of operations with respect to jumping or branching. So there is a variety of instructions. So the instruction set itself is going to dictate how good your instruction, how complete your instruction set is, and the more number of instructions you add to that, the complexity of the instruction set architecture increases. You don't want to start off with discussing, very complex instruction set. We will start off with simple instructions, and then we'll build on that on Thursday. Now, let me ask you one question before we move forward. Is it going to take me so if I have 32 registers in my register file, and if I have a 32-bit address space for my memory, which one is going to be faster for me? To read a register or to read a memory location? Which one is faster? But memory is very big, right? I have 30. So if I'm searching for something in, say, 100 things versus 10,000 things, I'm searching for just one thing, right? So if there are fewer things to search from, that should be faster than, say, here, I have a bunch of, people in a room. If I had, say, 10 people in that room, then searching for one person would be much faster than if the room was filled with 1,000 people. Do you need to look through the bits in the individual registers? No. You wouldn't need to. So you're just looking for, all right, I want to access contents of a particular register, right? So, right. So 32 registers versus 32-bit address space, which can go up to 4 gigabytes of address space. Right? That's a big difference. And it turns out that if you want to access the register file, it is 100 to 200 times faster than accessing the memory, right? And in general, if your memory is smaller, the access to that will be much faster. For example, if you have a cache memory, which is expensive but small, the access times to that are much smaller than access times to a hard disk. That is pretty big, right? So we will keep note of that, because sometimes you might want to interact with the memory. You may have to do that, and sometimes you may not have to interact with the memory, right? So one option versus the other could be faster and slower. All right, so now let's talk about the MIPS instruction set. Where are the registers stored? So they are part of the memory itself, but they are a separate entity, right? They are supposed to be uh, providing the processor a very, very quick access. So they're supposed to be closer to the processor, but it could be anywhere. The point is that they are smaller in number. All right, so let's talk about MIPS instruction set architecture. I don't think I have talked about MIPS. This MIPS is different from the million instructions per second. This MIPS is a microprocessor without interlock or interlocking pipeline stages. And when we get to pipelining and how you could have interlocking or without interlocking, we'll take a look at that when we discuss pipelining. Right now, think of it as one instruction set. There are others, right? There is a x86 instruction set architecture. There are other variations as well. This is the instruction set architecture we are going to use for Kenos. Now, you might wonder, is this extremely old or is this relevant to me? My answer is yes, it is absolutely relevant to you because MIPS instruction set architecture is used in Sony PlayStation. It's used in Nintendo switches. It's used in Broadcom chips. It's used in Cisco routers. It's used in laser printers from HP. So even though things that we are going to talk about over here might seem like, oh yeah, this is too elementary, the goal is to do things simple because they give us speed and they give us organization. Now, oh, by the way, if you want to learn more about this, just simply go to mips.com and look for MIPS 32. There are lots of variations about of this MIPS instruction set architecture, which is sort of a modern reduced instruction set computer, modern RISC architecture. MIPS 32 is what we are going to follow here. There is also MIPS FPGA. There is MIPS 64. There are other variants of MIPS ISA that you can look up on MIPS.com. But if you go to MIPS.com and look for MIPS 32, you will see all the details, like everything in detail. I didn't even recognize. It's right here. MIPS is microprocessor without interlock pipeline stations. Right. So MIPS register. Each register, like I said, there are 32 registers given to us that we have access for. Each register is one word. One word is 32 bits or 4 bytes. And we know what is 4 bytes. Each byte, 1 byte equals 8 bits. And you can also say, let's say one word, right? So you can also write this as 2 half words. So one word or 2 half words or 4 bytes or 32 bits. That's how much each register has. Register is what? It's a placeholder for bits. So it can hold up to 32 bits. Not up to, I should say, only 32 bits. And there are 32 such registers that are meant for a particular purpose. So there is a purpose for each register, and we'll talk about that. Now, question is, why not 64? Like I said, the smaller the space, the faster it's going to be. So why do we need MIPS 64? Well, if you have to go for MIPS 64, the only reason for that is for the instruction set to be more advanced, to include a lot more instructions into it. You can have a lot more instructions by going to 64 registers, but for our class we will use 32-bit. Now, variables reside in the registers as far as possible. Again, why? Because if I keep things inside the register file, I'm going to be doing things fast. The moment I need to load things from memory or store things to memory, that's what is going to slow me down because I'm accessing this big memory. And registers, like I said, are grouped by roles, and we'll look into all those details in a little bit. So that's all my registers in MIPS. There are 32 of them, register number 0 all the way down to register number 31, giving me a total of 32 registers. Each of them can hold 32 bits. Now, the first register here, which is called the 0 register, it has a constant value of 0. That means this is one register actually you cannot mess with. This is a constant. It is going to remain constant forever. The users do not have the right to change the contents of this register. So only the 0 register is sort of like, okay, it's going to be the same all the time. What does it have? It has a constant value of 0. What does that mean? It is filled with 32 zeros. A bunch of zeros. Why do I need that? Well, it is very useful to me to maybe initialize certain variables using this zero register. And I'll talk about that, how you can use the zero register to your advantage. Next, you have AT, which is register number 1. Notice the dollar sign. That's what we are going to use to indicate that we are talking about a register. Dollar followed by the name. And sometimes you can also do $1, $2, $3, $4, and so on to indicate the dollar sign for the register followed by the register number. By the way, you don't have to memorize all of these things because they are all these minute details which you're not expected to remember them, but in general you should know, okay, what do they stand for, what are the groups, what are the roles, and so on. All right, so AT is reserved, and that's for the assembler, and that's register number 1. V0 and V1, those are two registers, register number 2 and 3. They are used for results and expression evaluation. So when you are using, say you're calling a function, and the function is going to need two things, right? When you call a function, what do you pass to the function? You guys have written many C codes or code in any programming language. When you call a function, what do you pass to the function? Parameters, right? Also called as arguments. So when you call a function, you pass arguments to the function, and those are going to be those 4 registers there, A0 through A3, numbered 4 through 7. But when you pass parameters or arguments to a function, you're also going to be expecting a return value, right? So those results or return values from a function, that's what that is used for, V0 and V1. There are many temporary registers used. There are 8 here and there are 2 more over there. So all these temporary registers, let's highlight the temporary register. Temporary is there and then more temporaries. So all these temporary registers, we can have more than 4 arguments. We are going to have to manipulate things in order to get that to work. So temporary registers, why do I need this? Well, you are going through a bunch of operations. Sometimes you want to hold some value temporarily into a register. You might not want to save it, but you might want to hold it temporarily, right? That's for the temporary. Like I remember from the first activity when you were swapping contents of three variables, right? A, B, C, I don't remember exactly what it was, but you were swapping contents of 1 to 2, 2 to 3, 3 to 1. You could have done that with a temp, right? 1 to temp and 2 to, and so on. So that temporary space is essentially used to carry out the function, but you're not interested in what it's holding at every point. You're not going to be interested in storing that value. So those are your temporary registers. We are going to use those often. They're also saved registers. These are registers that are used to actually save your results. Maybe you want to move things to memory eventually. Then you're going to use these 8 saved registers there. There are 2 registers that are reserved for the kernel, OS kernel, K0 and K1, $26, $27. Those are the 2 numbers. And there are a bunch of registers used for as a global pointer or stack pointer, frame pointer. And if you're calling a function, it should also know where to resume instruction operation. So that's the return address. We can store it over there. So as we look through examples, you guys will see the usage and the reasons why these are present. These are available to us in our MIPS architecture. But that's it. That's our set, 32 of them. This is summarized on the green page in the Patterson and Hennessy textbook. And if I go to that over here, it looks like this. And I've also uploaded a document in resources on Piazza. Under resources, under general resources, I have uploaded a document, which is this particular file. And as you can see, all of that is available here, right? Which register, what's the number, what's the use, all of that is mentioned over here. And apart from that, there is also every little detail that you will need to write up an instruction. So on the left, you have the name or the mnemonic, part of the pseudocode right here. What is the format? We have 3 different formats for MIPS instructions, R, I, and J. This one is R. I'll talk more about that. What is the operation and what is the op code or the function code for that? So you will need this particular MIPS reference sheet all the time. If you're working with MIPS architecture, you will need to refer back to this multiple times. As we are doing examples, I'll show you guys how to check into this. All right, let's come back here and move forward. Let's talk a little bit about memory organization. And the main reason why we need to kind of understand this is because of this particular difference. If I go back to this slide here, my memory is say 8 bits each, right? I said each memory location is 8 bits. However, my registers are 32 bits each, right? So this is 32 bit here, but this is 8 bits here. So if you were getting things from memory or pushing things to memory, then in one place you have 8 bits and the other place you have 32 bits. So clearly there is a need to explicitly point out which 8-bit or which byte goes where, right? But for now, we know that each register is going to have 4 bytes. Each byte could be each memory address. So when you have MIPS memory, you are obviously talking about a memory in which you can have a 32-bit address. So you are doing things that are byte addressable. You guys see that? So whenever you look at memory, for example, all of this is memory. You have at each location, what do you have? You have 8 bits here, you have 8 bits there, you have 8 bits there, you have 8 bits there, and so on. And if you have 32 bits for an address location, in total you have 2 raised to 32 bytes with byte addresses 0, 1, 2, 3, and so on. These byte addresses are right now expressed in decimal. So at address 0, you have 8 bits. At address 1, you have 8 bits, and so on. Now, if you were trying to interact with the register file that is of 32 bits, suppose you were calling things into memory, into a register. So suppose you are moving things from memory to a register. Of course, you are going to need a 32-bit word to be filled. So how is that going to work? Well, each 32-bit word is going to be a combination of 4 8-bit bytes or 4 bytes, 1 byte being 8 bits. So if you look at what does this guy have? Well, address 0 or word 0 is a 32-bit word that has address 0, 1, 2, and 3. So those 4 bytes, one after the other, go into this. Now, a question that should come up in your head is, does it go 0, 1, 2, 3, or does it go 3, 2, 1, 0? How does it go? So for this is word 3. This is address 3, address 2, address 1, address 0. In which order do they fill up the 32-bit block? Well, that now depends on whether the format is little endian or big endian, right? So MIPS follows big endian, and we'll take a look at that. So it's actually 3210. It's 0, 1, 2, 3, big endian. So the last one goes all the way to the end, 3 there. another thing to note here, if you have addresses, these are byte addresses, by the way, the byte addresses are 0, 1, 2, 3, the next word is going to be what? Starting with 4 as the byte address, right? And this is going to be 8, this is going to be 12. So if you just look at bytes, let me fill out bytes. The word 0 has what? Word 0 has byte 0, 1, 2, and 3. And word 4 has 4, 5, 6, 7. Word 8 will have from 8, 9, 10, and 11, and so on. And if you look at closely, these are always going to be a multiple of 4 because they are 4 at a time. What is a property that you have seen before in terms of binary equivalent of these numbers? So if you look at 0 or 4 or 8 or 12 and so on, what is that one property that you can say as far as the value is concerned in binary? Last 2 bits are always 0. Yes, absolutely. So the last 2 bits are always going to be 0 because it's a multiple of 4, right? And we can actually use that later on. So if you want to, so even if you don't have the last 2 bits, you could get it by shifting left and putting 2 zeros in there. Okay, so you've got addresses here, 0, 4, 8, and 12. At each address, you have got a 32-bit word. Word 0 has all of these things. Word 4 has all of these things, and so on. So in total, what do you have? Well, in our memory, we have 2 raised to 32 bytes because we have 32 bits as our addressing scheme, and they are byte addressable. So if I give you a 32 bits, then I should be able to access any byte. Byte 1, byte 2, byte 3, byte 4. It is byte addressable as opposed to being word addressable, right? So you're not addressing words, you are addressing bytes within a word. You have the ability to address bytes within a word. In terms of words, what do you have? Well, if 4 bytes make one word, and you have 2 raised to 32 bytes, then you of course have divide by 4, you have only 2 raised to 30 words in total. Those addresses are what? With the first byte address as what? 0, 4, 8. The last one will be 2 raised to 32 minus 4. In terms of our byte addresses, our addresses will be 0, 1, 2, so on. Whatever you can address, whatever you can have with 32 bits. With 32 bits, I can go from 0, 0, 0, 32 zeros all the way to 32 ones. Right? So that's my 0 to 2 raised to 32 minus 1. Now, let's talk about that byte ordering convention. I touched on that a little bit some time ago. We'll see how things are done in MIPS, which is big endian, as opposed to doing things the other way, which is the little endian. So if you have word 0, which is byte 0, byte 1, byte 2, byte 3, and if you transfer this into a register, for example, how are things going to settle into that register? Is this going to go all the way to the front, or is this going to go all the way to the front? In big endian, this goes all the way over here. So you start off with this guy, the most significant goes all the way to the most significant space, right? That's what we are used to. All the way to the left is most significant. So whatever you read first, the first byte is going to be most significant. Then you get your second, the third, and then the fourth one will go all the way over here. And the same applies for the next word. So the second word, starting with the byte address 4, if you look at this, that's going to go over here. And then you have got 4, 5, 6, and then 7 over here, that goes over there. What would be the other way of doing it? Exactly the opposite, right? So in the little endian way, you start off with the least significant byte. Sorry. The least significant byte goes here, and then the most significant byte goes here. Right? So the last one is what is being pushed up. That's not what happens in MIPS. This is the one that we are going to follow in MIPS. So whenever you're trying to access something from memory and you're getting things into a register, for example, that's how things are going to work out. The first byte is going to go all the way to the front. The last one is going to go all the way to the back. Now, word alignment. That's also very useful to learn. Why? Because things are no longer byte aligned, right? So we don't have things that are byte aligned. We have things that are word aligned. Consider this situation. If you wanted to get byte 2, the byte number 2, what are you going to have to do? Well, you're going to have to fetch the whole word from where? From memory. You're going to have to fetch the whole word from memory in order to be able to extract byte number 2, which is why we have MIPS instructions such as load word. We don't have load byte, we have load word. So when you execute that instruction, you are loading the whole 32 bits, whole like word byte 0, byte 1, byte 2, byte 3, and then you can extract that particular 8-bit sequence from that. And also, if you so what if you wanted 2, 3, 4, 5? Can you do 2, 3, 4, 5? Or let's talk about 3, 4, 5, 6. It's called a unaligned word access. That kind of unaligned word access was recently introduced in MIPS architecture. In Intel-based architecture, it was introduced in, I think, 2010 or something. So pretty recently. But still, there is a way to get around that. Even if you want to get those 4 bytes, you could still kind of get word 0 and get word 4 and rearrange things to get those 32 bits. But that's not what we are going to do. Our operations are going to all be word aligned. Hopefully, when you guys look at examples and instructions getting executed, things should start falling into place. We have a small instruction set. I talked about the details. Details are in appendix of the textbook, but they're also summarized on the green page, the MIPS reference sheet, which if you have a printer accessible, I would encourage you guys to print that out and keep that handy. The design philosophy is simple and regular instructions, only one way to do a task. Now, this is talking about one way to do a task as opposed to many different ways of doing a complete operation, right? So of course, if you want to carry out a bunch of operations, there is going to be a faster way of doing things versus a slower way of doing things. There is going to be a way to do it in fewer number of instructions versus many instructions. What this is meaning is, suppose you wanted to add 2 numbers. There is only one way you can do that. You have to use the add instruction. That's what that means. Smaller hardware is faster, and we are also going to look at ways you can improve things for the compilers. So certain instructions are better suited as far as compilers are concerned to save time. We'll start with arithmetic instructions. Arithmetic and logical instructions are pretty similar to this as well. So we'll look at add, we can look at multiply, divide, and all that. But for our example, we will use add. So all arithmetic operations have 3 operands. Now, arithmetic operations, where do they happen? Whenever you are going through this list, it is useful to have this in context. You have a register file with 32-bit registers, and you have the memory, large memory, right? So when you are doing arithmetic instructions, you are kind of here. You are in the register file. You are working on registers. You are working on contents of registers, and you are storing the results in another register. So your world is register file when you are doing arithmetic or even logical operations. When you're doing other type of operations, for example, if you're doing load or store operation, then you would want to be able to talk to the memory. That's when you need to be at both places. But for arithmetic, your focus is on the register file. And there are some constraints with instructions. Let's take a look. The operand order is fixed. Your destination is first. All operands must be registers. Like I said, your world is here, register file. We are going to, simplicity favors regularity, which keeps things fast. So suppose you are trying to execute this C code. Very simple. You are adding the contents of variable B and C, and whatever the result is, you want that to go into variable A. So in C code, that's what you would write. Now in MIPS code, or you can call that pseudocode or MIPS pseudocode, you write this particular instruction. How does this relate to that? Well, let's take a look. Like I said, destination first, right? So destination first. Where is the destination? Things after getting added are going into A. But A is a variable right now. However, I have 32 registers that I could use. Well, I could use temporary registers for this. I could also use saved registers for this. But because I'm doing this as an example, this is not something that I'm doing as a temporary exercise. I'm just doing this as a saved exercise. So let me use S0. That's the register in which I want to store the results. That's what A is representing. A is representing the contents of the register S0. By the way, is there a way to find out what that number is? Let's go and check into the MIPS card. $S0 has the number 16. So that's what this is. What are you trying to do? You're trying to add. What to what? You're adding B and C, and the result of that addition goes into A. 32 bits added to 32 bits goes as a result into A in the form of 32 bits. Now, question is, what kind of numbers are these? Are they unsigned numbers? Are they signed numbers? What kind of arithmetic am I using to add? All these things are based off of 2's complement arithmetic. You guys in your computer organization or in your COCO class have seen 2's complement arithmetic, meaning you can represent positive or negative numbers in their 2's complement form, perform the addition or pseudo addition or subtraction, and then store the result as a 32-bit number in A, for example. So the arithmetic is carried out in 2C, and the representation is also in 2C. Questions here with this example? So what is going to be useful is for you to connect the two. One is C code and the MIPS code, right? The connection, that's what we are trying to establish here. Given a C code, are you able to come up with what is the 16 represent? 16 is the register number for S0, and then 17 for this guy and 18 for this guy. You ask a very important question. Why do I need this? Right? Why do I need that 16 and 17 and 18? Well, I need that because when I write things down to the machine language level, right now they are in assembly, right? When you look at MIPS code, that is at the assembly language. You are going to use a compiler to actually go down to the assembler to go down to the machine language, which is a bunch of zeros and ones. Can we write that line as $60? Yes, you can. Yes. So this is fine, and the other way is fine as well. Usually, so this is the norm. The norm is to use S0, S1, S2 for MIPS assembly, and then use 16, 17, 18 when you need to start talking about the machine language, because the way we identify these registers is by their number, right? At some point, you're going to have to write a bunch of zeros and ones to tell the processor to work on this instruction. That's when the numbers become relevant. And then this is 8. Very simple, right? Add this to this and then put the result back in the first operand. 32 plus 32 gives you another 32. All right, let's go to data transfer instructions. Actually, let me, all right, let's come back to that later. Data transfer instructions. Another type. This is not arithmetic. This is load word and store word. Why do I need it? Well, sometimes you have a number in memory. You want to bring that number from memory to a register file so that you can do some manipulation to that. In that case, you need to load the word, right? So load word, the purpose of load word is to load from memory to register file. Do the instructions in register file, and then maybe you want to store things back. For that, you need the store word. So for store word is store register file to memory. Not the complete register file, but I'm talking about a register, a particular register to the register to a memory location. Now, when you load word, what are you talking about? Memory and register file, right? How do you refer things in a register file? Well, we talk about registers, right? That's right there. $S1 is the register that we are going to end up in, right? So whatever you're loading from memory, it is going to get loaded into this $S1. That's the 17th register for it. It's a 32-bit register. Now, when you're talking about memory, what are you talking about? You're talking about an address, right? Where is that address? Well, I have to have a base address stored in S2, right? Let me use a different. S2 is a register which is 32 bits that can contain the base address. I'm going to add an offset to that base address to get the address from which I want to load. So I'll repeat this. You have a base address S2 in S2. The base address is going to be a 32-bit address to which you can add an offset. The offset is 16-bit. Once you add the offset to the base address, you get your address location from which you want to load from. So the way it is going to work is it is going to take that base plus offset and it's going to load the contents into register S1. Whatever was there at that address, it's going to load into S1. So on the right here, you look at what it means. Memory parentheses S2 plus offset. Where in memory? You take whatever you have in S2, you add offset to it. Whatever is there at that particular address, you put that in S1. For store word, things are going to be the reverse. Is offset always 16-bit? Yes, it is. So Branch and load are I-type instructions, also called as immediate instructions, and they have an offset field of 16 bits only. So that you bring up a good point. This also means that I have a limitation on how big or small my offset can be, right? 16 bits, you can only go as far as this, right? So that kind of limits the space over which I can perform that load operation. All right, store word, going to be exactly the opposite. You are going to take a particular register and store it to memory. I need to give the address for that memory location. How am I going to give an address? Exactly the same way as I gave the address in the previous one. Contents of a register and an offset. So when you add the contents, 32-bit contents of S2 register to this particular 16-bit offset, you get the address location in memory, the place you want to store what? S1. Right? So S1 will go there. Again, the address is S2 plus offset. That's the location in memory, and that's where you are going to be storing S1. So if you have, let's put two things here. One is register file, and then you have a big memory here. Load word is doing what? Store word is doing what? Load word is doing this. Store word is doing that. But no matter what they are doing, no matter which direction it is doing a 32-bit load or store. Now, I talked about word aligned operations a little bit ago, right? Let's put that in context over here. When you have a memory in which you have a bunch of 8 bits, 8 bits, 8 bit, 8 bits at a time, and when you load a word, you see, you're not loading a word anywhere but these locations. When you load the word, you are either doing byte 0, byte 1, byte 2, byte 3, or you're doing 4, 5, 6, 7, or you're doing 8, 9, 10, 11. You're not doing a load word that starts at 2. You see why that word alignment is important? And exactly the same way for store. Whenever you're storing something, you're either storing at 0 or starting address should be 0, 4, and so on. All right, let's see. Load and store are only instructions that can access memory. Like I said, that's the only two registers that are accessing the memory. We'll see the data transfer category on the green page. That's where the details will be. Now, an example here. What are we trying to do? In terms of a simple operation, we are trying to do G equals H plus the 8th index of A. A is some memory location. Inside that, the argument is 8. So we have a byte there, a byte there, a byte there, and so on. Eventually, we have A of 8. And suppose in order to work on this instruction, we are going to use, say, S1, S2, and S3. Let's just assume that. And let us say that S1 is the register that is indicating the result, G. S2 is the register that is indicating the operand H. And S3 currently has the base address of A of 0. So base address of A of 0 is the address to access this guy. However, we are not trying to load that guy. We are actually trying to load this guy, right? That's what we want to add. So what are we going to need to do? Well, I don't have A of 8 right now in my register file. When I do this addition, what does my addition involve? It involves 3 registers. 2 of them are source registers. The other one is the destination register. So everything needs to be in the register file. So I'm going to need to bring this to register file first by using the load word operation, and then I can do the addition after that. So, and this is a very good place to use the temporary register T0. So what I'll do is I'll do a load word T0. 32 is the offset. Where is this coming from? The base address is still S3, so that's consistent with my load word syntax. So I get the base address from S3, I'm adding 32 to it. Need to figure out why 32, because this shows up as 8. And then whatever is there at that location, I'm loading into this temporary register T0. The reason for this 32 is because every word is 4 bytes. So if you want to go up to here, that means you are going to need to do 8 times 4. That's how you're getting that 32 number. The offset is computed by multiplying things by 4. Right? So load word at byte address S3 plus 8 times S4 into the register $T0. Now, once you get things into T0, you can add to H, store in G. So let me color code this. This is G, this is G, this is G, this is G. Then what is H? This is H, this is H, this is H, that is H. A of 8 went into this plus this, right? And that's what you got over here. So why is this example useful? Well, suppose you want to do some arithmetic or logical operation. You have one number in the register file ready. You have another number in memory. How do you do that particular operation? You need to bring that to register file first, do the operation next. Sometimes you might want to have to store it back. If you want to store it back, then you need to use store word operation there. Next, let's try to put in into context what you have learned so far. For MIPS, loading words, we are loading words, but we are addressing bytes, right? So we are addressing byte 1, byte 2, byte. It's a byte addressable instruction set architecture. But when you're doing the loading operation, you're doing the load word. You're not loading bytes, you're loading words. Arithmetic is on registers only. So here are 4 examples. Addition you have seen earlier. In the similar manner, you have a subtraction operation that is laid out. The first one, as we said, the first one is going to be the destination. So this destination is that. And then because subtraction, we need to keep track of the order of the operands. S2 goes first, followed by S3. Again, you don't need to remember these details. These are, of course, in the MIPS reference sheet, and you can take a look quickly for subtract. Like subtract is right there. Subtract, RS minus RT. RS and RT are used for the source registers. If our offset was 34, would we? No. So it has to be a multiple of 4, right? It has to be a multiple of 4. You see this? Offset 8 times 4. It's going to be a multiple of 4. Right. So I'm going to talk a little bit more about this. Let us see if we have 0, 4, 8, 12, and so on, right? So those are my starting address word addresses. Could you do something like this? Add S1, S1, S2 for S1 plus equals S2. So yeah, S2 plus S1, you're storing it S1. Yes. No, a third register is not necessary. It'll take the current contents of S1 add it to S2, put the result in S1. And to do that, what about add S1, S1, S1? Yeah, so S1, S1, S1 would be take S1, double it, put the result back into S1. All of those things are valid statements. All right. Let's see. Subtract, we talked about that. Load word, store word. Now, if you wanted to, so the offset, if it is 0, what does that mean? That means that whatever you had in S2, you are moving into S1, right? So that's offset being 0. Let me in the later in a little bit, I will try to show you guys a MIPS simulator, and you are welcome to use that on your end. But I'll just do a simple demonstration so that you guys can see how the instructions work when you assemble them and when you actually run those instructions. Keep all the instructions to 32 bits. We have different formats for different instruction types. R, I, and J. We'll talk more about that in a little bit, because we are going to need to understand how the format looks for each of those instruction types. We will explore by an example. So the first thing that we are going to do is to take a look at an R type instruction. R type means register type. So we are looking at arithmetic operations, logical operations. All of those fall in the category of R type instruction. In R type instructions, you have a lot of fields. Each instruction is 32 bits. So this is an instruction, 32 bit. Where is this coming from? Well, that's the instruction register, right? So I'm assuming that my instruction register, part of which is operand specifier, part of which is opcode, all of that is 32 bits. Some of the bits are reserved for opcode, which specifies what type of operation are you trying to carry out. The next, because this is register to register operations, your world is register file. Everything is happening in the register file. And when you're dealing with only the register file, your operands are in registers, your destination is also register. So you need two sources so that you can do the instruction between them. And then as a result, you need to put the result into the destination register. How many registers do you have? 32. How many bits do you need to refer to each register? You have a total of 32 registers. So I would need 5 bits to access 1 out of 32 registers, right? So if I wanted to say S0 or S1 or S2 or S3, whatever, I need 5 bits to do that because there are 32 registers, right? And similarly for RT, which is my other source register, I need 5 bits there. And for destination, I have 5 bits again, right? So 5 bits because 32 registers. Next, shift amount. Well, why do we need shift amount? We need this particularly for the shift left logical and the shift right logical operations. If you wanted to shift certain bits to the left and pad the empty spots with zeros, or to the right and pad empty spots with zeros, you could use shift left logical or shift right logical operations. Otherwise, it is a bunch of zeros. Then the last field is the function code field. It is used because some operations have variants. For example, if you have add, there is also add u, or do the addition operation, treat them as unsigned numbers that you are trying to add. Addition, the other one is addition, unsigned addition. So because operations have variants, you also need those 6 bits to indicate function. Do I need 6 bits here? Do I need 6 bits here? Not necessarily. You are maybe adding more bits than necessary. The goal is to keep it consistent with 32 bits. It would be very awkward to have everything 32 but this as 28, right? So everything is being made into a consistent length. Let's take a look at that example for function. Like I said, addition, and I did add unsigned. Let's highlight add. Add is right there. The mnemonic is add. The format is R type. What is it doing? It is taking two registers, RS and RT, adding the contents and putting that into the destination register indicated as RD. Over here, the opcode is 0. In this case, you have a bunch of zeros in the opcode field, but the function code is 20 in hex. So you would do 20 in hex. What is the conversion to binary? You would express that in that 6-bit field function. Similarly, if you look at the other variant of add, it's right here. Add unsigned. So you have add u, it is still doing RS plus RT and then storing it in RD, but now it is supposed to treat the numbers in doing the addition unsigned way, right? Still opcode is 0, but now you have 21 as your function code. So that's an example of how those function bits would play a role. Let's go back here. So that's it. 6 bits for opcode, 5 bits each to identify the 3 registers at play, shift amount coming into picture for shift operations like shift left logical or shift right logical. By the way, this comes very useful in division or multiplication operations, right? If you do a shift left logical by 2 bits, what is that? Right? Shift left logical by 2 bits is equivalent to what? Multiply by 4. Absolutely. Right? So, and then of course, if you do shift right logical by 2 bits, that is kind of like dividing by 4, but then you have to have nice numbers because otherwise you will have to deal with remainders. So if it was a multiple of 4, then you could do that. All right, let's move on. All right, so hopefully that gives you an idea about how an R-type instruction looks like. Do I have to remember all this? Nope. If you go down on your first page, you can see this. The basic instruction formats on the green page, R-type instruction. You've got opcode, RS, RT, RD, shift amount, and function. Everything is laid out over here. And then there are I and J type instructions as well. We'll talk more about that in a little bit. So we are doing the example of this R-type instruction here. If you are trying to do this addition, we are adding 2 registers. Contents of S1 and contents of S2 are being added together, and the result needs to go into T0, for example. Now, whenever you do this, it is maybe helpful to do 2 things. You can take a look at C code. What would this be? This would be something like A equals B plus C, where A is sort of $T0, B is $S1, Could be S2 as well. It's commutative. And this is S2, right? So if you want to do this, then you're treating ABC as these three registers, and then in MIPS pseudocode, you're entering that. The thing that we have to be careful about is that the destination is first. So now let's talk about the numbers, because we have been talking about the number, register number, as opposed to a register name. This is where it comes into the picture. It's an R-type instruction, add, so it has all these fields. Opcode has 6 bits. What is the opcode for add? Let's go back, take a look. Looks like add has opcode of 0. Right? So it's opcode / function. So opcode is 0 for add. All right. So that means that I'm going to fill in 6 zeros over here, followed by RS and RT. These are my source registers. What are my source registers? S1 and S2. What are their numbers? 17 and 18. So I'm going to enter 17 over here in binary, 18 over here in binary, right? So simply, it is simply a decimal to binary conversion at this point. So what would be 17 as 5-bit binary? I think I need 16 plus 1, right? 2, 4, 8, 16. That's it. And then for 18, I need 1, 0, 0, 1, 0. And for 8, what do I need? 1. That's it. You guys see that? And then opcode is what? 6 zeros, 6 bits. Yes. 1, 2, 3, 4, 5, 6. Shift amount, 5 bits zeros. Function 32. All right, there's a problem there. Why? Because addition over here, it says that it is 20 hex, right? So when you take 20 hex and you convert it into decimal, you get 32. So this is 32 in decimal, right? 32 in decimal expressed using 6 bits in binary would be what? Let's see. 1, 2, 3, 4, 5. Will that do it? This is 1, 2, 4, 8, 32. Yeah, done. So this is your 32-bit machine code to carry out that particular instruction. You guys see that? So my goal is this, to connect C to MIPS pseudocode to machine language code. C to MIPS, that requires understanding. MIPS to machine language, that requires MIPS reference sheet. Right? Questions about this example? Pretty straightforward. All right, let's go to an I-type instruction. An I-type instruction, I stands for immediate type. I is immediate. Now, what if you wanted to do addition in a specific scenario? For example, you wanted to do add immediate, meaning you have one number in the register file, the other number is a constant. I don't need to look in the memory for a constant, right? I can provide that immediate number directly to the instruction. The result needs to go into a register file. That's an example of add I or add immediate, which falls under the category of I-type instruction or immediate type instruction. For specifying non-register operands, like the constant. This is also where the 16-bit offset address goes. So load word and store word are both I-type instructions, which require a 16-bit address. So for I-type instructions, this 16 bits, the last 16 bits, can be used either as the immediate or the constant, or they can be used as a address, like the offset address that we talked about. Still have 6 bits for opcode, no function here, so no variations. I need the 6 bits of the opcode to do all the variations. I have 2 registers, one is RS, one is RT. They are both source registers, and then the 16-bit offset or 16-bit immediate, so constant or part of the address. Let's take a look at an example. Load word. What am I trying to load? Whatever is there at S2 is an address, is a base address. Add 100 to it, which is the offset. Whatever you get after that addition, go look into that memory location for 32 bits, starting at that address, and load all of that into S1. S2 plus 100, whatever is there at that memory location, put that into S1. How am I going to indicate that? Well, first I need to look up the opcode for load word. All right, where is it? Load word, LW, right here. 23 in hex is the opcode. When you convert that into binary and express that as, let's do it right here. How many bits do you have? 6 bits, right? So 23. What is that? 0010, 0011, right? That's binary equivalent of 23. What are the 6 bits? The 6 bits are right here. 10 followed by 0011. That's right there. 100011. And if you converted 23 into decimal, that's what you would get, 35. So that's how you get to the opcode. Next, you have RS and RT. What do I have? RS and RT. 18 for the base register, 17 for the destination register. RS, what is it? S2. Where is S2? Right there. What is the number for S2? 18. That goes over there. I have to look at all of these over here, by the way. You see this? RT equals, what is the memory? RS plus the sign extended immediate. That's your offset. So let's spend a couple of minutes talking about this. Why do a sign extension to the immediate? Well, immediate or the base address, how many bits do I have for that? You guys, we talked about this, that it is 16 bits, right? So if something is 16 bits, this guy, without the extension, it is 16 bits, right? The immediate or the base address is 16 bits. How am I going to add something that is 32 bits to 16 bits? Well, I need to make it 32 consistent, and then I can add them, right? So what I do is I take that immediate address or the offset address, the offset address, do a sign extension. So if it's a positive number, I continue adding ones to the most significant bit. If it's a negative number, then I keep doing 1 like I keep adding ones to the most significant bit. I make it into a 32-bit sequence, and then I can add it to another 32-bit sequence there. That is going to be my address. That is going to go into RT, right? So RS is base address, RT is the destination. That's how I know. Which is why the choice over here for RS is 18 and RT is 17, because RS corresponds to S2, RT corresponds to S1. That's color code. S1. And then, of course, if you want to find the 32-bit instruction for this, you already did the first 6. 18 converted to binary will give you those 5. 17 converted to binary will give you those 5. 100, which is the offset converted into 16 bits, will give you that. Questions here? what is the immediate number exceeded the capacity of 16 bits? It cannot. That's the limitation. So whenever I'm trying to load word or store word, or there are other places where this immediate number or the limitation of 16 bits come into picture, it essentially limits your range. So if you are really very far off from the base address, which is also contents of a register, then you actually have to change the base address itself in that case. All right, let's move on. Add immediate. Like I said, there's a I type instruction. The reason why I need this is because one of my operands, one of my numbers, is not in the register file and it's not in the memory. It's a constant. It doesn't need to be in the memory. It's a constant. So in that situation, I don't need to use add. I can use add immediate, which is a I type instruction. What am I doing here? My C statement is whatever is in B, that's a variable, so I'm going to need a register for that, add it to 100 and then store the value in the destination register A. Or variable is A, but I will need a register for that. So in this case, I'm using T0 for A, that's my destination. B is in another temporary register T1, and 100 is 100. I don't need any place to store that. So the instruction for that is add immediate, $T0, $T1, source, this is the source, 100, constant, add those two, put the result into the T0 register, right? These two get added and then store in this. It's not stored. It's part of the instruction. So it's going to access the instruction itself. So let's see. That's a very interesting question. So I'm going to take a look at this. Oh, sorry. You see, the instruction register is right here, right? So that 100 is somewhere in there. That needs to go into the ALU. So that one number comes in, the other number is here, and it's going to add. Sorry if you answered it already, but if you did, let's see. Can a register be both the destination and operand? Yes, it can be. So when it is being treated as operand, that's where it's going to start, right? So think of it in terms of time. It is going to take whatever its value is, and then when it ends up into the register again, that's your destination. So it's going to change within that, within the duration of that instruction cycle, it's going to change contents. So absolutely, it can be both destination and operand in one instruction. All right, so I think we talked about, right, so the ALU needs to get two things, right? One register and one constant. The constant is going to come from the instruction register, and the control unit needs to facilitate that. The control unit needs to facilitate that one end is coming from the register file, the other end is coming from the instruction itself, instruction register itself, add it, and then we'll see what we do with the result. It goes back to the register file, the result. So hopefully that answers the question about but to clarify, the IR has from -3 to somewhere as constant. No. So the instruction register is whatever we want it to be, right? So for example, if I was doing this particular operation, add operation, this would be the contents of my instruction register, right? So the the control unit is going to look at all these 32 bits and appropriately carry out the instruction. All right, I know it's an R type instruction. Where should I look for the destination? Where should I look for the sources? What is the shift amount? What is the function code? So the instruction register, I won't associate a range with an instruction register, right? I know it's 32 bits, but what are those 32 bits depends on the instruction that you're trying to carry out. So for this instruction, that was the 32-bit sequence. Now, when you come to the offset, right, the address or the immediate constant, that's where it is going to go, right? So when you have 100, you would convert that into a 16-bit binary string and put the bunch of zeros and ones in that field. So the control unit, when it looks at that particular opcode, it says, all right, I recognize this as a load word instruction. I need to treat this as the offset. I recognize this as an add immediate instruction. I need to recognize this as the immediate constant and be able to add it. You guys see that? So the opcode sort of that needs to be decoded by the control unit first before all of this can happen, which is why decode instruction is your second step, right? Like after fetch instruction, the next step is to decode instruction. All right, so add immediate, we looked at that. So opcode, we can keep going back and forth between the MIPS card here. If you look at add immediate, it's right here, second one. Add immediate, add I. Take the contents of RS, add it. Oh my gosh. I'm running into some trouble here. I'm going to reduce the brightness part. Okay, so I'm going to take add immediate, right? So I'm going to take whatever is in my RS, add it to the sign extended immediate value here. That's my immediate constant. After I get the result, I'm going to put that result back into RT. What is the opcode? 0. What is, opcode, there's no function, right? This is the immediate. So it requires opcode and it requires the 16-bit immediate. So opcode is what? 8 in hex. So that's what we have here. 8 in hex, which is also 8 in decimal. Shouldn't be a problem. That goes there. RS 9, that is for T1. RT, the destination register, 8, standing for T0. And then the constant 100. This might be off topic, but is your computer running on low power? It is on extremely low power, and I'm going to have to figure out an alternative, but I'll wait for it to crash. All right, so that's your add immediate. I also want to go through some other instructions here. Branch is also an I type instruction. There are two variations of branch instruction. Branch when equal and branch when not equal. So branch when equal, what does that mean? I'm going to compare two registers, contents of register 1 and contents of register 2. And if they are equal, then I will branch to L1. What is L1? L1 is an address that I'm going to go to, right? In C, you might have written instructions like go to this, right? Like a label. And that's where your C code will jump to. This is something similar. So L1 is essentially an address that you are jumping to. How are we specifying L1? Because this is a I type instruction, we are specifying L1 as a 16-bit address, right? So we are going to, I'll show you guys what that L1 is. It actually is going to do this. If I look at branch on equal, it is going to take the current contents of program counter add 4 to it, which means that it is looking at the next word, add the branch address to that, which is a 16-bit value, and upload that new number into program counter. So essentially, I was running a bunch of instructions in sequence. Now I have a condition here in which I'm trying to compare the value of two registers, and if they're equal, I'm going to update my program counter with this new address, PC, old one, plus 4, because if branch address was 0, it would have been the next value in the program counter anyway, right? So it goes 0, 4, 8, and so on. With the new branch address, it's going to add to PC plus 4, and that's where it's going to jump to, right? Again, branch addresses are 16 bits. So how far away you can go from program counter is going to be limited because of that 16-bit. So think of L1 as a label that you're jumping into within your program. Branch when not equal. So sometimes this BEQ is useful, and sometimes branch if not equal is useful. So if you're trying to compare two contents here of two registers in your register file, and if they are not equal, you jump to L2, right? So branch to L2 if not equal. Again, I-type instructions, so they have to be consistent with the format. Opcode, RS, and RT are your source registers, and then the last one is the relative offset that is provided using 16-bit address. We'll take a look at more examples. Another example. Here you have an if condition. If I equals j, perform this operation. H equals I plus q. Now, in order for me to translate this C code into a MIPS assembly code, what I'll do is I will associate I with $S1, J with $S1, I with $S0, J with register S1, and H with register S3. So what is it doing? Check if I equals J, and if it is, execute this particular addition operation. This can be written in this form. Let's go through this to understand. Branch when not equal. What is it? S0, S1. If they are not equal, jump to L1. What is S0? S0 is I. S1 is J. So this is saying if I is not equal to J, then jump to L1. Where is L1? Right here. It's a address identifying the next instruction to be executed, right? So if it is not equal, it is going to jump over this addition to L1. Do you see that? But if it is equal, what is it going to do? It is going to execute this, then execute. It's going to be one after the other, right? Remember, the last step in the instruction cycle was what? Update program counter so that it points to the next instruction. So by default, if it is equal, it is going to add S0 to S1, put the result in S3. Exactly that. H equals I plus J. You guys see that? So the example that is written over here is to check for equality, but the MIPS code that we have written is checking for inequality. But they are both doing the same thing. What happens after L1? It doesn't matter. Whatever follows in terms of instructions next in my overall task. You guys see that? How should I know if I should use BNE or BNQ while encountering an if operation? Well, it depends on convenience, and it depends on whether using one or the other can help you reduce the number of instructions. So in some scenarios, actually in most scenarios, compilers prefer checking for inequality rather than checking for equality. So BNE in general is used a little bit more often because it can reduce the tasks for the compiler. But I cannot generalize it for every scenario though. You will be looking at whether it helps you reduce the instructions or not. All right, jump instructions. What is this? This is simply, I am working on something right now, right? PC is whatever value it is. I'm working on these instructions right now. I want to, without any condition, I just want to jump to a new location and then start executing programs over there. So J-type instructions or jump instruction is your third category. R, I, and then the last one is J. In J, you simply have 6 bits for the opcode for identifying this as the J-type instruction, followed by a 26-bit word address. Hold on. We said whatever you need to work on has to be in the program counter. If I assume that my program counter contains an address that needs to be executed next, it has to be consistent with the addresses in my memory. I said I have a 32-bit address space in my memory. So program counter also has to be 32 bits. I'm talking about 26 bits here. Where are the remaining 6 bits coming from? Let's take a look. First, we take this 26-bit field and we multiply by 4. What does that mean? We do a shift left logical twice. Why are we doing this? Because we know that program counter has to be a multiple of 4, right? PC followed by PC plus 4, followed by PC plus 8, and so on. So because we know that, I only need to provide 26 bits. And once I have the 26 bits, the first step I'm going to do is move 2 times to the left and pad it with 2 zeros, so that is kind of like making it a multiple of 4, right? That's multiplying by 4. That gives me a 28-bit number. Once I have this 28-bit number, I still need 4 bits. Where is that going to come from? Those 4 bits are going to come from the 4 most significant bits of of PC, current PC. So suppose your program counter is having a particular 32-bit address. What is that? That is the address of where you can find the next instruction to be executed, right? But it will have 4 bits, right? Those are the most significant bits of the program counter. I can use those 4 over there. I can use 26, move to the left by 2, that's multiplying by 4 to get the 28. So in total, what did I get? I got a 32-bit number to which I can jump to. So in other words, because I know it is a multiple of 4, and because I know that it is going to be relative with respect to where PC is right now, I don't need to give the total 32, I just need to give 26. You see that? All right. Right, I'm running a little bit short on time here. I'm gonna pick up a little bit pace. Here we have a if then else C code, checking whether I is not equal to J or not. If I is not equal to J, do this addition operation, else do this subtraction operation. This is your C code. The MIPS code for this is written over here. But we are doing it with branch when equal, right? So we are saying that branch, so for this to work, I need to associate I, J, and H with, with something. What is H? Let's take a look here. H is my destination, so that should be S3. I is S4, and then J is S5. You guys see that? So branch when equal, check whether S4 equals to S5 or not. If it equals, jump to L1. It's right here. What does it do? Once it jumps to L1, it does a subtraction operation. So it's carrying out this. Something similar to the else condition over here, right? Not equal, check for not equal to. What does else mean? Else means it is equal. If it is equal, do the subtraction. That's what this is doing. branch if equal to L1, carry out the subtraction. In the other case, what if it was not equal? Well, if it was not equal, it would simply go to the next instruction, which is the addition, which would carry out this guy. But once it carries out this guy, if I did not have a jump instruction here, it would go to the subtraction, which is going to spoil everything for me, right? So if after I do add, I need to jump to L2 so that I jump over that S2 instruction. So this is an example where you see branch when equal, add, jump, subtract, all of those things. So test for opposite condition is more efficient. Like I said, branch when not equal is efficient in most cases. How do we develop a simple loop? Suppose we are trying to do a set on less than instruction. So this is inequalities and how you have instructions for that. Usually in combination with BEQ and BNE, you can say the C code over here is what? If S1 is less than S2, go to L1. Okay, so if you had to carry out this instruction, you can do that using these two MIPS instructions. Set on less than, what does that mean? If S1 is less than S2, set T0 to 1, all ones, 32 ones, else T0 is 0. So let's take a look. If S1 is less than S2, that's what this condition says. If S1 is less, it is going to set it. Set on less than. And once you either set T0 to all ones or not, you can use that for the branching. So you are comparing over here T0 with all zeros. If it is not equal, jump to L1. You guys see that? All of this is one C statement here. So let's ask this. When does this jump? When does this jump? Well, S1 less than S2, right? The contents of S1 register, if they are less than S2, then it will jump. Okay. Does this match up with our MIPS instruction? Let's check. Let's assume that S1 is less than S2, right? So what is going to happen if S1 is less than S2? If S1 is less than S2, then T0 is going to be all set to 1, right? All ones, 32 ones. Which means the branch when not equal, is it not equal now? This is all zeros, this guy is ones, so it is not equal. It will branch to L1, right? So this is exactly when it will jump, when S1 is less than S2. If it is not, then it will not jump. It will simply go to the next instruction. So that's another way you can use the zero register to your advantage. We talked about that already, right? If T0 is not equal to 0, that is S1 is less than S2, go to L1. We talked about that. A switch, case switch statement. So suppose you have a switching statement where you are comparing for case 0, case 1, case 2, case 3, and so on. In that case, you can build a jump table array, meaning you can have different cases when k is 0, give an address for task 0. When k is 1, give an address for task 1. Simply, you are going through a lookup table where you have a bunch of addresses to start working at when a condition is met, right? So, for example, we are going to use the jump register instruction. Jump register $T1 essentially means you are going to jump to address in register T0. What does that mean? You are essentially changing the contents of the program counter to whatever is there in $T0. So $T0 could be the address of task 0 when we are switching based on k equals 0, right? So if k equals 0, you do task 0. What is task 0? I will write a code in the memory starting with a particular address. I will provide that address to my jump register instruction, and I'll be able to jump like that. So that's your case switch statement that you can carry out using the jump register instruction. So this is essentially a summary slide for our discussion today. We looked at a bunch of instructions, some arithmetic, some I-type instructions, and some jump instructions. All of those, the add and subtract fell in the category of R-type. The next 4 fell in the category of I-type, and the last 2 fell in the category of jump instructions. Their meanings are given and the formats are provided over here, but you should really look at the MIPS reference sheet for the formats in detail. Now, when you're doing the activity 5, I know that we are short of time here, but I'm hoping that you guys can use the office hours from 8 all the way to 10. So 2 hours of office hour help sessions in the evening. 8 to 9, there's a TA office hour. 9 to 10, our undergraduate student assistant is going to help out. So I'm hoping that you guys are able to finish it tonight. Please take a look at these notes for activity 5. It's not particularly difficult. I'll leave you guys to complete that. I think I tried